So interpreting graphs of linear functions. And we're going to look at, first of all, some terminology. Okay, because when we're interpreting graphs, we're going to use some words, we're going to use some terms, and so we want to know, well, what do these terms mean? Okay, so first term is, well, what's a linear function? And so we kind of just mentioned what that is. It's going to be any straight line that is not vertical. Any straight line that is not vertical is going to be a linear function. Okay. When we work with graphs, when we interpret graphs, oftentimes we're interested in knowing, well, if my input value is this, what would my output value be? Now, depending upon what other information we're given, if we're given an equation or if we're given the table of values, sometimes we can see those points clearly. If we're looking for values that are within that graph, okay, within the graph, if we're looking for values that are sort of shown within the graph, we're doing something that's called interpolating or interpolation. To interpolate means to find a value that is within the graph. I guess I can finish that off on the far right hand side here. Okay, to find a value that is within the graph. Okay, so that's inter, right? Inter something means, you know, within. Okay, extra. So extrapolate, extra means beyond, right? Like to do extra stuff means to do stuff that's beyond what you normally do. And so extrapolate means to find a value that is beyond the graph. Okay, so difference there, within and beyond. Excuse me. And so sometimes to extrapolate, we have to do kind of one of two things, right? Number one is, can we draw the line further? Sometimes we can, but sometimes we can't. And so when we can't, we actually have to use the equation, or we have to do something else. Even same thing with interpolate, right? Sometimes to interpolate, you can sort of estimate, right, a particular value, but in order to find that more specific value, sometimes again we have to use the equation. Okay. So two more definitions here, or terms. Okay, one's called the x-intercept and one's called the y-intercept. So the x-intercept is the place where the line, and we might as well say where the linear function intersects, and typically we're going to see where it crosses the x-axis. Okay. Technically, the term intersect doesn't mean cross. It simply means touch. Okay. But you can think of, you know, if you're doing your driver's test and you think about, you come to an intersection. So at an intersection, do both roads always cross? The answer is no. Sometimes one just kind of butts up against the other, right? That's T, intersection. So it's where they touch. But when we're working with linear functions, obviously the line is going to cross it. Okay. Now the x-intercept, one thing to note about the x-intercept, because it's the place where the function crosses the x-axis, what we know there is that the y value is equal to 0. Okay. Because the x-axis, that's that whole axis there, right, on your sort of your graph. And in terms of, well, what's the y value there? The y value goes up and down, and the x-axis has a place where y is always equal to 0. Oops, that doesn't come apart. And then the last one is, well, what's the y-intercept? Okay, so it's kind of a similar sort of definition. All right, this is going to be the place where the linear function intersects the y-axis. And then conversely, we would say that the x value is 0. Okay. And this y-intercept also has a kind of unique particular characteristic. Okay, so this y-intercept is sometimes also known as, right? If you ever heard the term AKA, AKA stands for also known as. So the y-intercept is also known as the initial or fixed amount. Okay. Yesterday we kind of looked at an example. I think it was either driving a car or renting a hall for a party, right? And then whenever there's an element that is a fixed cost, a fixed amount or an initial amount, that's our y-intercept. Okay. Now, how much room do you have there? You got some room left on the bottom of that page? Good. Because I want to add sort of two more things, kind of right side by side. And I want to simply call it the difference between. Okay, the difference between. We're going to write sort of two things. And it really is important when we look at interpreting linear functions, or really any kind of functions, but it's the process of interpreting. We want to know what's the difference between a generic function and b, a function in context. Okay. A generic function and a function in context. So underneath here, we're just going to write a couple of things for each of these. Right? Well, what's the difference between a generic function and a function in context? Well, this would be an example of a generic function. Y is equal to 50 plus 3x, or 3x plus 50. Right? That's generic. Okay? It's generic because we're just using x and y. Right? The function in context could be something like this. C is equal to 50 plus 3n. And you might look at that and you might say, well, I don't really see a difference in that other than the variables have letters. And so this in context, the variables have meaning that is relevant to the context. And so that's kind of the first thing that we do, right? Is we use different variables that are relevant to the context, right? So as an example, right, C could represent the cost of something, and N could represent the number of something, right, that we're buying. Okay, so the variables have meaning, which is relevant to the context. That's kind of the first thing. Okay, because it's in context, context basically means that there's a story here, right? Cost and number, what's going on? Like what is this story about? So context, when we have a function in context, it's important to understand that there is a story here, and we need to understand what's going on so that we can answer some particular types of questions. And then in terms of context, there's kind of one last thing that we're going to write down here, and that is that the domain and range usually have restrictions that the generic function doesn't have. Right? The domain and range usually have restrictions that the generic function doesn't have. Okay, and so when we turn over the page, there are a couple of examples that we'll kind of look at. We'll walk through the first one together totally. Lots of questions there. We'll walk through it together and sort of see how we address some of these issues. Okay. So questions before we begin, before we move into that first one. Okay. All right, so the graph here shows the fuel consumption of a scooter with a full tank of gas at the beginning of a journey. And so you can see that our independent variable here along the bottom is the variable d, which represents distance. And then the dependent variable is represented by the capital letter V up at the top of that y-axis there for volume in terms of liters. Okay, so we kind of have a story going on here. It's the volume of gas in a scooter, as obviously we're kind of driving along here. So the first question simply asks, what's the coordinate of the y-intercept? So remember, y-intercept typically refers to the vertical intercept. Because you might say, well, where's the y? We don't have a y here. Well, generically, y is the vertical axis. So our vertical intercept, right, is occurring here. And so we say, well, what's the coordinate of this point? Right? So coordinate means that we have to use an xy pair. Okay, well, the value of that y-intercept, so the y value is 8, and of course the x value is going to be 0. Right? 0, 8. Now, the second question kind of has us interpret what that y-intercept means, right? It says, in this context, what does this point, what does the y-intercept represent? Now, you kind of have to do two things here, right? You have to sort of say, well, it is 8, and the units for this 8 are liters. So the y-intercept is 8 liters, okay? But what does it represent? Okay, so how much fuel is in the tank at the beginning of the journey, right? Because the distance driven is 0, right? And so this is the amount of fuel that's in the tank at the beginning of the journey. Now, you could assume something about the tank. You could assume that the tank is 8 liters large, right? Because the tank is full. You could, right? But it's better to say, because we don't know if maybe the tank is actually 20 liters. All we know is that this is the amount of fuel at the beginning of the journey. Do not simply go, the volume is 8 liters when the distance is 0. Right? That's kind of, yes, that's sort of a wooden interpretation. But you want to say that the volume, right, or there are 8 liters of gas at the beginning of the journey, right? That's what that means. Of gas in the tank at the beginning of the journey. Okay. All right, next question. So first two questions were related to the y-intercept. Next two questions related to the x-intercept. Okay. So question number 3 here says, what's the coordinate of the x-intercept? Okay, so again, it's going to be an ordered pair. And we know that the y value of the x-intercept is automatically going to be 0. And so we look along that x-axis, or the horizontal axis, right? And we see that the intercept there, the place where it's touching down, is 200. Okay, so that's our coordinate. Our coordinate is 200, comma 0. Okay, and again, in this context, what does this point represent? So again, we say, well, the x value, the distance is 200 when the y value, the amount of gas remaining in the tank, is 0. Okay, so how do we sort of represent that? What does that mean? Right? So the 200, what is it, kilometers? 200 kilometers is either A, it's the length of the journey, or it's just that's how far she can go on a tank of gas. Right? So 200 kilometers is either the length of the journey, since there's nothing else on this graph to indicate that she goes any further, this person goes any further, refuels or anything like that. So 200 kilometers is the length of the journey, or the distance traveled on the tank of gas. Right? So interpreting has two parts to it, right? It's understanding, well, what is that numerical value, and then giving it meaning. Okay. Now, before we look at the next question, I want to actually look at that graph itself, right? The volume of gas in a scooter. And we can see that it starts at 8 liters when the distance is 0, and then it goes down to a distance of 200 when the volume is 0. And then underneath there, there's a little question, right? The question says, can we accurately determine how much fuel is remaining after driving 60 kilometers? Right, so if we look at the sort of the grid lines on here, right, we're going from 0 up to 100. Now, can we accurately determine how much fuel is remaining after driving 60 kilometers? This is a question of interpolation, right? Because we're trying to read something that is within the graph. Okay, so thumbs up. Yeah, we can accurately tell, and here's the number. Right? Suddenly, whoops, no, your thumbs went down, right? Because we can't accurately tell. We can estimate, all right? We can kind of be approximate, right? Because here's, well, this is 50. We could maybe tell how much at 50, but for this question, at 60, the answer is no, we can't. We can't accurately tell, not based on the graph. So can we come up with an equation that we could use? Because if we could, well, then that would be much better. Then we could get a more accurate picture. So that's basically what the next couple of questions are having us do. So in order to know what the equation is, remember that linear functions have a particular type of equation, right? They're going to have an x and a y, generically speaking, that will have an exponent of either 0 or 1. And we sort of saw from yesterday's lesson that if you have a slanted one, we can determine the equation of that function. Right? We might have to go back to sort of see what that looked like. Generically speaking, that function looks like this. Y is equal to some number times x plus some other number. So I don't want to smile. I'll put number again, but they're not the same numbers. Now, question is, what did that number in front of the x represent? So from the notes from yesterday, the number in front is the rate of change. Absolutely. Excellent. So rate of change times that number, right? Because rate of change, this is what's changing. If x is changing, then here's what it changes by. Plus, and then the question is, well, what's the second number? And going back to yesterday's lesson, that's the initial amount. Okay, so this is our, I'll just kind of put it as IA. It's our initial amount. So, in order to answer this question, we need to know these two things. We need to know what the rate of change is, and we need to know what the initial amount is. Now, one of those is really easy. It's the initial amount. All right? So that's our y-intercept. So we know that our initial amount is plus 8. And that's why the question that comes before this is says, what is the rate of change? So that's what we have to now determine. What is the rate of change? So remember, rate of change is the change in the y values over the change in the x values. By looking at this graph, would we say that it's linear? Right? It is, right? And so what we can do is, in order to determine that rate of change, we can use any 2 points along this whole line. Any 2 points. Well, when I look at this graph, I can really only clearly tell, like for sure, 2 points. The y-intercept and the x-intercept. All right? And so for that, I'm going to use those 2 points. I'm going to use the x-intercept, that's this one down here, and then the y-intercept, this one up here. So by looking at those 2 points, what has been the change in y? What did we start at? What did we finish at? Right? 8, right? We started at 8, we're down to 0. So the rate of change is 8 over, and now what about the change in x? What did we start at? What did we finish at? All right, started at 0, finished at 200. Okay, so this is going to be 8 over 200. Okay, except there's kind of one thing that's sort of a little bit different here. Now, 8 over 200, you can change that to 0.04. Right, that's the decimal that would be equivalent there. The only thing is it's technically not a positive number. Right? It's technically not a positive number because the change in those y values is going down. And because the change in the y values is going down, this is technically going to be a negative number. Negative 0.04. Right? So that's the rate of change. Now the next question says, well, what does it represent? Well, to know what it represents, what we need to do is we need to use the units of y over x. Right? We need to use the units to know what it represents. So we look at, well, what are the units of y? Well, so the units of y are liters. And then what are the units of x? Well, the units of x are kilometers. So this stands for 0.04 liters per kilometer. So what do you suppose it's talking about? Considering the story. Right? The story here was volume of gas in a scooter. So this is 0.04. Kind of, right? Now, mileage, right? Mileage typically is what's your distance per unit of volume? So that would be like kilometers per liter. So when it's the opposite way, liters per kilometer, we call that consumption. Right? How much fuel is required for a particular distance? That's the same basic idea, right? You're absolutely right. This is called fuel consumption. And so you could say it's similar to mileage. Okay, but typically, when you're talking mileage, right, higher numbers are better. 100 miles to the gallon, right, versus 50 miles to the gallon. Okay, 100 miles to the gallon is better because a gallon of gas, I can go way farther. That's great. So bigger is better. In terms of consumption, lower is actually better. All right. Because if it takes me 10 liters to go 100 kilometers or only 2 liters to go 100 kilometers, which is better? Well, only 2, right? Yeah. So with consumption, smaller is better. With mileage, larger is better. So it's the same kind of concept here. So in terms of our equation, right? Our equation here, determine the equation of the function, we want the rate of change here. So y is equal to negative 0.04x plus 8. Now that's generic, right? Because it's just x and y. So now let's put this equation into context. And then it also says put it in function notation. Okay. So in context, the only thing we're going to change here is we're going to change the y to a different letter. We're going to keep the negative 0.04. We're going to change the x to a different letter. And then we're going to still keep the plus 8. So now, based on maybe the graph, what letters should we be using here? All right, V and D. The volume is the same as where the y is. And the D would be the same as where the x is. And so the volume is negative 0.04 times D plus 8. And now it does say put it in function notation, so we'll simply put that little bracket thing there. The volume is a function of the distance driven. And now we could, if we wanted to, we could graph this on our calculator and do some fun things with this. Okay, questions so far? All right. Next question down says, use the equation to find the amount of fuel remaining after driving 60 kilometers. So now we can very clearly, very accurately answer that interpolating type of question. Right? Use our equation now to find the amount of fuel remaining after driving 60 kilometers. So driving 60 kilometers, that's going to go in the place of the D, right? The distance driven is 60. So what we're asking for is find V of 60. What's the volume after we've driven 60 kilometers? And so now that we've got this equation, we know it's going to be negative 0.04 times D, which we plug in as 60, okay, plus 8. So you can use your calculator. 60 times 0.04 plus 8 works out to be 5.6 liters. Okay, so there are 5.6 liters of gas remaining after we've driven 60 kilometers. No way we could get that accurate from the graph, right? We could kind of say, it's somewhere between 5 and 6, but we can't accurately determine what that is. Okay. And we could answer that question, we could answer any question sort of using interpolation, right? That we could read within the graph. Now, 2 more questions, right? And we could actually ask a whole pile of questions, but 2 more that we'll specifically be looking at here. Number 1, is the data continuous or discrete? Okay, so remembering what it represents. Is this data continuous or discrete? So I'm going to go back up to the graph and sort of look. Well, what are we talking about here? Oh yeah, distance. Okay, distance on that left-hand side, and then volume, or sorry, distance on the bottom, volume on the left-hand side. Is distance continuous or discrete? Can you fill in the interval between any 2 points? All right, if it's yes, then it's continuous. So between 100 and 200 kilometers, can we fill in the entire interval? Well, how about between 100 and 101 kilometers? Yeah, right? Distance is a continuous kind of characteristic. Okay, so the domain is continuous. What about the range? What about volume? Is volume continuous? I would hope so. Otherwise, the gas, as it's flowing through, kind of goes ka-chunk, 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 right? But no, the gas just flows, right? Volume changes between 8 liters and 7.9 liters, right? So both of these particular concepts, both of them are continuous. Okay. Now, even if they were discrete, would it be wrong to use a solid line? No, because there's a lot of points, right? There's a lot of distance points in there, so we would still use a solid line. Now, here's a really important question, right? When we talk about domain and range, right? The domain and range of any linear function, okay, except for horizontal lines, the domain is always any real number. And then the range, typically, if it's a slanted line, is any real number. Because, you know, you take a slanted line, it goes forever left and right. It goes forever up and down. However, in the context, right? And remember what we wrote down on this page at the bottom. In context, the domain and range usually have restrictions, right? Because in the story, what does the domain represent? What does the range represent? So in this story, the domain is the distance. Okay, so two questions. Number one, can you have a negative number for distance? No, because when you're driving, you're driving. You don't drive negatively. Even if you're backing up, you're driving a particular distance. So distance is never negative in this particular context. And then is there a maximum distance that we drive here? And the answer is yes. The maximum distance we drive here is 200 kilometers. So in this context, our domain is going to be, okay, and first of all, we're going to use the letter D for distance instead of X, right? D for distance. And then since we have a smallest number and a largest number, use those two numbers, excuse me, and put the distance in between. So the distance is going to be between 0 and 200 kilometers. And we could, if we wanted to, we could also say that the distance belongs to the set of real numbers if you want. It's not necessary because it's going to be there by default, right? Because we can travel any decimal value for distance. But here's the restriction, right? The restriction is that the D has to be between 0 and 200. Okay? And that's what we see on the graph. That's what the graph shows us. And then similarly for the range. The range represents volume. Well, there's a maximum number, right, for that volume. And then there's a minimum number for that volume, right? We can't go negative amount of liters, right? What does that do? Suck your tank? And, I don't know, it doesn't do that. So your volume, now, and again, you can use V here, less than or equal to 8, and again, greater than or equal to 0. Okay, so that's the sort of the range, you know, the limits of what that volume is. And again, if you want, we can say that the V belongs to the set of real numbers. We can take any decimal value in between there. Okay. Now, it's really important to remember that anytime you have a context, right, that you have to think about these restrictions. Because you could say, well, couldn't we graph this on our calculator using this function, right? The answer is, well, yeah, we can, right? This function would look like this, negative 0.04x, because in your calculator, we just always use x and y, right? Plus 8. And then in order to get a graph that's going to look relatively similar to this, we need to change the window. All right, because remember, the window basically describes, you know, how far left and right, how big of a piece of graph paper do you want, right? And so in terms of the window, if we want it to match the one that's here, right, we can see that our piece of graph paper goes, well, actually it goes a little bit left of 0, and it's okay to put a number that's left of 0, and it goes up to about 300. So for our X window, if I kind of take the numbers that are there, it's kind of going from about negative 75, that's where that third little tick mark here to the left would be, up to 325, right? Because there's actually one little extra box past the 300. And the scale here would be, well, we see these little grid lines going up pretty much every 25, right? In terms of the Y value, okay, so the Y value, okay, there's the 0. Each tick mark looks like it's going up by 1. So the bottom part here is actually down at negative 3. and then it goes up to what looks like 11 going up by 1s. And so now when I press graph, I should see a picture that looks kind of like that, right? And so when I press graph, yeah, I do, except for one thing. What's different between the calculator screen and that actual graph? Right? It continues. It goes past that left edge. It goes past that right edge. And so here's where you have to understand that on that calculator, that's a generic function, right? Y equals x, plus 8. And so in context, we actually have to stop when we get to that x-intercept, and we have to stop when we get to that y-intercept. Okay? All right, and so that basically answers all the rest of those questions. Now, here's another cool thing that you could do with your calculator. We wanted to know how many liters were in the tank when x was 60. Right? On your trace feature, right? When you press trace, it puts a little spider on your graph. You can now press any number you want for x. So I want to press 60. When x is 60, what's the y value? Hit enter. Bingo, there it is, 5.6. So now I can more quickly answer a question and I don't have to actually do the calculation over and over again. How much gas is left when I've gone 85? Okay, 4.6. How about if I've gone 92.7 kilometers? How much gas is left, right? So you can use your calculator to answer some questions rather quickly. Okay, so and throughout the rest of this course, we'll kind of learn a few more things about the graphing calculator, and so that when you start 20-1 or 20-2, you're going to be using your graphing calculator a lot more. Okay, so that's kind of a first example of interpreting graphs of linear functions, this particular linear function. Any questions that popped up in your mind that didn't get answered as we went through this example? Okay, so here's our second example, and I'd like you to work through, excuse me, both this example and the next example, so these two examples in sort of the last 15 minutes that we have. Okay, and then tomorrow we'll basically start hopefully with, this is the sort of the last example that we'll kind of sketch. I think you've got this grid on your, do you have this grid on the back side of your page? Yeah, okay, and so this is basically where we'll finish off tomorrow. Okay, so work on these two examples here, and if we have time today, we'll kind of quickly go through them, but we'll finish this up tomorrow, and that'll be the end of this particular lesson. Okay?